Okay. How do I balance it? I split it in half. I use my 4 steps. Here's the 4 steps. And then I combine them together and get rid of electrons, and that's my acidic conditions answer. To get my basic conditions, I find the H pluses. I add the same number of OH minuses to both sides. H plus and OH make water. I simplify, there's my basic conditions answer. So you'll notice in class we're going to do a couple more, 2 more I think. I always follow this pattern. It'll always work. Okay, and you can watch also the most recent video, 2 videos ago when I did over how to balance redox. So let's do that. Step 1, we're going to separate out the reaction into things that look similar to each other. So, Cr2O7, put the chromiums together, and then put the carbon species together. Okay? And we should probably figure out which one's the oxidation half reaction, which one's the reduction half reaction. So I'll get a different color pen, brown. Okay, I will do the easy ones. This is +3. Okay, what's the charge or oxidation state on the chromium right there in the dichromium? I'll give you a hint. It's a plus something. What's oxygen? -2. Okay, so with 7 of them, it's -14, right? Okay. So you have to think, what -14 is -2? Probably 12. And since there's 2 of them, each one is 6. Okay, so we did it in our head. You could do it on paper too, but you get +6. If you don't, make sure you do practice of these. Okay, so that one's oxidized or reduced? Yeah, if it reduces in value, then it's called reduced. So by definition, this one's by elimination, the other one has to be oxidized. Okay? All right, so now let's balance it. I'll get a different color pen. We're going to go through each of the 4 steps with both of these reactions. So let's try the top one first. Step 1, you balance whatever's not oxygen or hydrogen. In that case, that's chromium. There's 2 chromiums on the left, so I better have 2 on the right. Step 2, you balance the oxygens with what? Water. So there's 7 there, I better add 7 here. Because I need 7 oxygens on each side. You can't just add oxygen, you can't just add O2, it doesn't work. Okay, next. Step 3, you balance hydrogen with H+. Oh, there's a question up there, I think.
Yeah, I'm sorry. Can you explain again why that one is reduced and why that's oxygen? Just a quick explanation.
Oh, yeah. Okay, how do I know what's oxidized and reduced? One's oxidized, one's reduced. 50-50 chance, first of all, right? Second, I just really had to do one of them. Find the charges. I didn't do it for carbon. Because when I found this is 6 and that's 3, it reduced in value. Thus, the chromium one is reduced, going from 6 down to 3.
Okay.
Is that okay?
Yeah.
So if that's reduced by default, this one must be oxidized. So you don't even need to find the numbers.
All right.
Okay.
That guy right there.
You're pointing at something. Oh, yes, this guy, yes. Where did I put what? Oh, I haven't even got there yet. But we'll get there in a second as soon as I finish everybody else's question. Yes? This is going to be in basic solution. That's right. Basic solution. Yes? Why does it matter? Because your only 2 choices are acidic or basic, and they're different answers. You'll see why as we do the problem. Okay. Step 3 is hydrogen. We balance hydrogen with H pluses, not just a neutral hydrogen. So now getting to your answer, there's right now 14 H's here. So I need to put plus 14 H pluses on the left-hand side. Now my H's are balanced. Step 4, I balance the charge with what? H plus. Okay, I'll give you a few moments head start. What's the charge on the left as is right now, and what's the charge on the right? Got like 10 seconds. Okay, what's the charge on the right? Plus 6. There's 2, 3 pluses. So it's 6 on the right. You see that? On the left, what is it? 12 plus 12 because it's 14 H's, so plus 14 minus 2. So 14 minus 2 is 12 on the left. So if I have 12 here and 6 here, which side are my electrons going to go on? First of all, right or left? The left-hand side. And how many do I want to put there? 6 electrons. That makes the charge equal on both sides. In this case, plus 6 on the right and plus 6 on the left. So as long as it's the same, I'm cool. I'm done with the reduction half reaction. If there's no questions, I'm ready to move on to the oxidation now. Okay? Oxidation half reaction. Step 1, what atom am I going to balance first? The carbon, yeah, whatever's not oxygen or hydrogen. There's 2 here, so I need 2 of those. So I have the same number of carbons on both sides. Step 2, I balance oxygen with water. And so, which side of the water is going to go on, right or left? Yeah, there's 1 oxygen here, but there's 4 here. So I need to put 3 waters over here to make it a total of 4 oxygens on both sides. What atom do I balance in step 3 now? The hydrogens. Now I'm to hydrogens. The H pluses will go on which side, right or left? The right. How many hydrogens are on the left? A total of 12. 5, 6, plus another 6. It's a total of 12. 12H plus. Fourth step, what do I balance? The charge with electrons. So I'll do the easy one. The charge on the left is 0. What's the charge on the right? Just 12, because there's 12H pluses. So it's a plus 12 on the right. So our electrons are going to go on the right or the left? Definitely the right. And I'm going to add 12 of them, so in this case, it has a charge of 0 on both sides. They're both the same. Okay, you need to talk with your partner to debrief what just happened? Okay, I'll give you a minute. If you have a question, please raise your hand. Question's a little more difficult than medium, so you don't give it so much fancy. Any questions? Raise your hands. Why is there 6 electrons on the right? Okay, we'll do that when people shut up. Okay, here we go. The question was, why is there 6 electrons right here? Because before that was there, I had plus 6 here, and then 14 minus 2, or 12. So 12 and 6. If I subtract 6 from 12, I'm left with 6 on the left-hand side. It's the same now. Is that okay? Yeah. Okay. So this is a little bit more difficult than medium, so it's not an easy one because there's big numbers. Okay, notice hydrogens and electrons are on the same side on both problems. Also notice the electrons are on opposite sides on the different reactions. That should happen. Okay? So that now, when I add up my what reactions? My simultaneous reactions that happen at the same time. I'll get a different color pen now. We'll go for blue. What must cancel? The electrons. Yeah, so I'm going to multiply the top by what? 2 and the bottom by? Yeah, nothing really, just a 1. Because if I multiply the top by 2, that'll give me 12 electrons on the left. Right now, on the second reaction, I have 12 electrons on the right. So if I add them, the electrons will cancel. So now, let me write out all the reactants first. Oh my. So, 2 Cr2, make sure I don't miscopy something here, plus 28H plus, and then I've got a C2H5OH from the second reaction, and I've got 3 waters. I think that's all the reactants. I dropped electrons because they cancel. And then all the product now, I think I have 4 Cr3 plus, I have 14 waters, and I have 2 CO2s, and I have 12 H plus. If I copied everything correctly, I'm almost at my acidic answer. Whoever asked what's the difference between acidic and basic, I'm almost to my acidic answer, except what do I need to do? I need to do a little simplification, meaning, see how I have H pluses on both sides? I should simplify. So subtract 12 from 26. Hopefully that's something like 16. Is that right? Okay. And then I have waters on both sides, so subtract 3, and that'll give me 11 waters on the right-hand side. So I just rewrite the same reaction with my new simplification. 2Cr2O7, the dichromate ion, plus 16H plus ethanol, C2H5OH. That goes to 4Cr3 plus 11 waters, plus 2 CO2, carbon dioxide. This is now my acidic conditions answer. Does anybody remember, how do I know this is an acidic answer? What's here that I see? Yeah, the H plus. See the H plus? Since that's here, that indicates to me that this is an acidic conditions answer. It better be, because that's what the process I just went through. Because acid is an H plus donor. So if you see H plus, it says. So this is my acidic conditions answer. Okay? Now, I didn't ask for acidic conditions answer. I asked for the basic conditions answer. So how do you solve that? Well, what you do is you locate your H pluses. Here they are, right there. I'll circle it in brown. Okay? You locate your H pluses and find the number of them. I have 16. I want to get rid of my H pluses to make it basic. So the way I do that is to both sides, I add hydroxide ions. So to the left side and to the right side. You might wonder, how many do I add? I added the equal number as I have H pluses. So if there's 16 of these, I've got to add 16 hydroxide. Okay, so I'm adding that to the right and to the left. It'll cause my H pluses to drop out. So I won't have an acid answer anymore. So what's going to happen, let's rewrite it. Cr2O72 minus. The H plus and OH will become what? Just water. 16 waters. Not 32 waters, 16. Plus C2H5OH. There's my right-hand side. My left-hand side is now Cr3 plus 11 H2O, plus 2 CO2, plus now 16 OH minus, because I just added it to both sides. I'm almost at my basic conditions answer. What do I need to do first? A little simplification of what molecule? See how water's on both sides? So I'm going to subtract off 11, and I think that'll leave 5, finally, on the left-hand side. So I'll rewrite this answer again with my new simplification by dropping out the extra waters that I don't need. 2 dichromate ions plus 5 waters plus an ethanol goes to 4 chromium 3 ions plus 2 carbon dioxide molecules and 16 hydroxide ions. And this now is my basic conditions answer. How do I know, what's my clue that tells me it is basic? Yeah, these hydroxides right there are my base. By definition, that's base in Chem 2A. Okay, so there, can you see how the answers are different? Asked me earlier. Okay, so you need to read the question and see, is it asking for acidic or is it asking me for basic? Yes. To get to basic, do you have to go through acidic conditions? Yes, in the way I taught you in class. There are other methods, but I think this is actually the simplest. So this is what I highly recommend, unless you like another method. So I need to now write out a reaction. I want to balance it. I want to put the state symbols in, and then I want to make it a net ionic equation. Okay? So this is a pretty typical exam question. We'll do examples like this in class as well. Okay, so how does this work? Okay. You need to write this out. So barium 2 plus, nitrate is that. Ammonium is NH4 plus, phosphate is PO4 3 minus. So you need to write, okay, barium nitrate, I need 2 nitrates. Ammonium phosphate, because of the 3 minus on the phosphate, I need 3 ammoniums. So I have a plus 3 from the ammonium and a minus 3 from the phosphate. There's my reactants. Those are mixed in solution. What kind of reaction is this? This is a double replacement because I have 2 ionic compounds mixing. What does that mean? They're both going to switch ions. So step 1 of a net ionic equation is writing the products. I'll write them down here, where the barium will go with the phosphate. And because barium is plus 2 and phosphate is minus 3, I'm going to have 3 bariums and 2 phosphates. So 3 bariums are plus 6, 2 phosphates are minus 6, so that'll be neutral. And then I'll have an ammonium nitrate. Ammonium's plus 1, nitrate's minus 1, so they'll go together, 1 and 1. I need to do what now? Balance. So I'll start here on the one with the most subscripts. 3 bariums, 2 phosphates, and that'll cause me to have 6 ammonium nitrates. So now it's balanced. That's step 1 of my net ionic. I write the reaction and I balance it. Step 2 of the net ionic equation is to find the state symbols. Okay? So here, if you're taking the exam, you need to pull out the back page of the exam, which looks like this. Something like that. Okay. Barium nitrate. Which bullet applies? We're going to go through each one. First bullet, it's a nitrate. That'll be aqueous. Okay, what's the next one? Ammonium phosphate. Which bullet applies? Yeah, you could say the first and the fifth, but the first one, they're in order of importance. So the first one's more important than the fifth. And ammonium, NH4 plus, is aqueous. So you got 2 aqueous so far. Next one is barium phosphate. Which bullet? Barium phosphate. The fifth one, a phosphate. Any questions about why it wouldn't be another one? It's a phosphate, yeah. Yeah, okay, good. That's exactly what I thought people were thinking. It's not the third one because the barium listed there is an exception to the sulfate. So it's barium with a sulfate or rose. Calcium with sulfate, strontium with sulfate, barium, lead, or mercury with a sulfate in particular. Not in and of itself. That's true for any of the exceptions listed. So the halide 1 second bullet has to be with one of those 3. You can't just have a lead and apply the second bullet. Yeah. That's right. When it says in the 4th and 5th bullets, except above rule, which one am I referring to? All of the ones above them. Every single one. Okay. So the barium phosphate, because of the fifth bullet, is a solid or a precipitate. Okay, ammonium nitrate, which bullet? The first bullet for the ammonium and the nitrate, so that one's aqueous. So we have AQ, solid, AQ. The first two you could actually have done differently. Just by reading the question, it says they're in solution. So they're aqueous. That's what the question says. Okay, so you could have done it that way too. All right, so we've done step 2 of the net ionic. We did the state symbol. Step 3 is to do the electrolytes. Is there anything here that's not a good electrolyte? The solid, that's it. The solid's the only one that's not a good electrolyte, because solids are not good electrolytes. Even though it's ionic, it's a solid. So the rest of these, I'm going to split up into their ions. Oh, there's 3 bariums. There's 6 nitrates. Oh my gosh. Too many N's. Okay. 6 nitrates over here. There's 6 ammoniums. So all the strong electrolytes I'm splitting up into solution right now. All right, I think I got them all split up and written out. Now I want to see if any of them cancel. And a bunch of them do. There's 6 nitrates that cancel with 6 nitrates. There's 6 ammoniums that cancel with 6 ammoniums. And what I have left is my net ionic equation. I'll rewrite it. 3 barium, 2 pluses. A what state symbol? Yeah, any ion is aqueous. Plus 2 phosphates, aqueous, goes to barium phosphate. Solid, that one's a solid, we knew that from before. This is the net ionic equation, and its balance is totally done. All right, I got a practice example here. A limiting reactive problem is recognizable because you have information leading to moles of more than one reactant. In this case, mass of 2 reactants, and it could be more, but of 2 reactants that lead you to moles, and it causes you to do 2 stoichiometry problems. Okay, now there's some weirdness. It asks me how many moles of ammonia are produced, and it tells me the mass. So let me read the question to you so you can see, and this is pretty normal limiting reactant problem. It says 33 grams of the ammonium chloride and 33 grams of the calcium hydroxide are reacted to produce 5.25 grams, according to this reaction. How many moles of NH3 are produced? Why is it giving me the mass here and just asking me the moles? What mass is this? This is what's called the actual yield. This is an experimental yield. They're asking me to calculate in moles here the theoretical yield. Okay? So if we give you a mass of the products, it seems kind of weird because they kind of ask you what the mass of the products is. The given one is most likely the actual yield, meaning what you got in lab. The one they're asking for is theoretical, which is going to be a number greater than 5.25. Or equal to, possibly. Okay? So you'll see as we work it out, I'm not going to use this number for a long time. Okay, I'm not going to use this number here for a long time. All right, let me show you how this will work. How do you do a limiting reactant? You pick with one of them to start with. So let's start with this one, I guess. 33 grams. I want to find moles of ammonia. Okay? So I go, well, I need the molar mass. I think I wrote that down. I use a periodic table. I got 53.49 grams. Okay? Now I have moles of the calcium hydroxide. Step 2, use a molar ratio. There's 1 mole of the calcium hydroxide for every 2 moles of the ammonia. That's where I'm going, is ammonia. Last step, go to what they asked you for, which is moles, so I'm done. And I calculated this ahead of time, I think. Oh, I wrote the wrong number here. It's 74.09, sorry. 74.09. Yeah, 74.09 right there. Okay, I got 0.891 moles of ammonia. Okay? Now I'm going to do this question again. But for the, starting with ammonium chloride. That one also starts with 33 grams. Its molar mass from the periodic table, let's get this right, that was a 53.49. Now I'm going to use a molar ratio to get the moles of what I want. There's 2 moles of ammonia for every 2 moles of NH4Cl. And this turns out to be 0.617. Okay, when I look at those two, I've been calculating the same molecule. Which one's the correct answer, top or bottom? The bottom one, the smaller value. So the limiting reactant was the ammonium chloride. The ammonium chloride, NH4Cl, was the limiting reactant. The next part of the question says, find the mass of the reactant in excess. So the one in excess was the calcium hydroxide. At 33 was too much. Okay, 33 was too much. I actually used less than that. I want to know how much less I actually used. Okay. So grab my pen. I'm going to start with the correct answer. Start with the correct answer. Now I'm going to make my way backwards to the reactant in excess. So that's the calcium hydroxide. So I use a molar ratio, 1 mole calcium hydroxide. 2 goes out of the parentheses. There we go. For every 2 moles of NH3. So there's my molar ratio. I want mass in this case. So it's still the 74.09 grams per mole for the calcium hydroxide. And this turns out to be, let's see what I got, 22.9 grams of calcium hydroxide. I want to think for a second, am I okay with this answer? Yeah, that's okay. This is the amount I actually used. This is the amount I've actually used. That's less than the 33. So I was right. 33 was too much. I actually used around 23. So at about 10 grams too much. But I want to actually calculate that that number. So I'm going to go 33 grams. This is the amount I had minus the amount I used. And this turns out to be 10.1 grams of calcium hydroxide. And this is the leftover, or what we might say remaining. So I had 10.1 grams left over. Okay, that was the answer to the second part of the question. The third question, I'm going to twofer here. What's the percent yield of ammonia? What's the percent yield? Now we're going to go, if I rewind a little bit, now I'm going to use this number. The 5.25. You're going to see how. Okay. Oh, yeah. Okay. So, what's the percent yield? That's going to be 100. The actual amount divided by the theoretical amount. The actual amount is 5.25 grams. So that's how much in lab I actually made. But I could potentially have made more if things didn't go wrong for me. So I potentially could have made 0.617 moles of ammonia. I need to change that to grams. So that's 17.01. I don't know if I wrote that number down exactly, but it's around 17 grams per mole. Let's double check if I wrote it down. I think so. About 17.01 grams per mole for ammonia. And then I need to multiply this number by the 100 still. Don't forget your 100. And for percent yield, I got 50%. That means the 5.25, I actually could have made double that. So I could have made about 10.5, theoretically. But actually, I just made 5.25. Okay? So they gave me that random 5.25. I don't use it until I get to the percent yield part of the question. And that's pretty common for us to do in a question. Anything? Anybody want to ask me about that? I have a base and an acid. So more specifically, I could have called it a neutralization reaction. That's a type of double replacement. Hey, just for funsies, strontium hydroxide, strong base or weak base? Strong. How do you know that? It's on that table I showed you. HF, strong or weak acid? Weak. Why? It's not on the table I showed you. That's it. It's on the table, it's strong. Remember that. You've got to know that table. If you need a little refresher, that table is in your textbook at the, I think, the beginning of chapter 5. Let me just flip to it real quick so I can refer. It's on page 36 in the middle of the page. All right, so this forms strontium fluoride and H2O. I need to balance it. I need a 2 there, and a 2 there will do it. Okay, so there's my reaction written out. I've balanced it. You could do a net ionic on this, by the way, after you get the state symbols. I'll tell you, all 3 of these, if I tell you all 3 of these are aqueous, which one of these 3 is not a strong electrolyte? This is just bonus fun. Which one of these 3 is not a strong electrolyte? 1, 2, or 3?
3.
2 is not a strong electrolyte because, what? It's a weak acid. Weak acids, even if aqueous, are not strong electrolytes. Okay? So this is one you would not separate out into. Okay, that's not what we're doing, but that was just fun. Okay, 1 molar. Let me just make up some numbers here. Okay, this is a pretty typical, what we would call stoichiometry for sure, but titration problem. You know it's titration because it involves molarity basically. And the second reason you know it's a titration, it's only dealing with the reactants. Usually in titration problems we don't care about the products. So you'll see we're dealing with the reactants. We'll ask you about one of the reactants. We might even give you information about that one. So you see how I give you 2 molar of HF? And I ask you the volume. So you might know a little bit, but you're asked about it as well. How do you do this? The same way you do any stoichiometry problem. You start with the one that's fully known. That's the first one. You change it to moles. Let's do that. You might say, okay, let's go 50 milliliters. And then I know 1.0 molar, that's 1 mole per liter. That's molarity, is mole per liter. And you want to cancel out the volume to get to moles, but it doesn't quite work because you're in the wrong units. So what you would do is do just a little conversion. And notice what happens now. The milliliters will cancel, and the liters will cancel. All I'm left with is moles. That's the first step in any stoichiometry problem. Second step, molar ratio. Let's do the molar ratio next. The molar ratio, I want to go to HF, so there's 2 moles of HF for every 1 mole of SrOH2, strontium hydroxide. Okay, so that's the second step, molar ratio. Last step, go to what you're asked for, whatever the requested unit is. Now this is interesting. Okay, let's cancel out those moles that cancel first so you can see this. So the moles of strontium hydroxide cancel. Okay, I have moles of HF. I don't want moles, I want volume. So I'm going to use molarity as a conversion right now. See that 2 molar? I'm going to write it upside down. 2 moles per liter. Why did I do that? Well, yeah, so I can get liters. I cancel the moles. I have liters. And then it depends what units you want the volume in. If you wanted the volume in liters, I'd be done. However, usually they're going to ask you this in milliliters. So I'll just show you to be continued right here. Times 1,000 milliliters per liter. And you get your answer in milliliters. I don't know what it is because I just made it up, but that would be it. Okay? Any questions on this? Yes? Oh, I'm so glad you asked that. Can you use the equation M1V1 equals M2V2? Does anybody know the answer to that?
Yes.
Okay, so half of you right now are correct. Either yes or no. You cannot and should not. Now, I'll say some caveats to that. When you go to tutoring center sometimes, or sometimes in high school, they tell you you can use it. There's a couple, sometimes it works. Okay, sometimes it actually does work. So first of all, the M1V1, M2V2 goes for what kind of problem? A dilution. So this is stoichiometry titration, first of all. But it works if it's in a 1-to-1 molar ratio. In this case, see how it's a 2-to-1 molar ratio? It won't work. And because it kind of annoys me a little bit, I usually pick questions like this. Okay? Yeah, you have to do the stoichiometry. Okay? It does work, you're right, if it's a 1-to-1 molar ratio, kind of by chance, because you're avoiding the molar ratio issue. Yeah. So I understand because you see it a lot in kind of tutoring, whatever. Yeah. That's a good. How do you know to use M1V1 equals M? I would never use it if it's a reaction, first of all. If there's no reaction and molarity and volume are changing, then you're going to use it. Because that means you're diluting something. The molarity is going down, say, the volume is going up. Then use it for sure. You see a reaction and I'm curious about more than one compound in the reaction, I'd recommend not using it. Yeah. You could just go wrong. That's the danger. There's so many reactions where it's not a 1-to-1 molar ratio. Yeah. Yes? That's fine. Yeah, you could do that. So, what's your name? Katie is saying is, notice I converted to liters and then back to milliliters. If you just drop those two conversions, you actually could do that, and that's totally fine. Then you're working in millimoles, but that's totally fine. Yeah, you can do that. And in Chem 2B, you're actually going to do that a lot. Okay. In this case, I have the overall reaction up at top, and I have my simultaneous reactions 1, 2, 3, and 4. This is actually also a test question before. Most of these that we're doing were all exam questions. Okay, so you know. 2 questions I can ask on simultaneous. What's the intermediate? And then what are the multipliers for reactions 1 to 4 to add up to the overall? So let's do the easier part of it. What's the intermediate? Or intermediates? Oxygen, water. Yeah. So notice the intermediates are anything that's down here that's not here. So the intermediates, O2, there's 2 waters, notice that. H2O liquid and H2O gas, or liquid water and steam. Is that everything? Oh, the B2O3, right? Is there anything else? Did I get them all? I guess I got them all. Okay. Now how do you solve this? as far as the multipliers go. Okay, for the multipliers, what I do, I have a two-step process. Step one, I match my overall reaction with the ones down below. So I'm look at boron, H2, and B2H6. Which one of those appear twice on the whole page and no more than twice? So boron, is that a good candidate? Yeah, that appears only in the overall in the first reaction. How about H2? Is that a good candidate? Yes, I think so. It appears in the overall and reaction 3, only twice. How about the B2H6? That's also a good candidate. It appears in the overall and reaction 2. So I'm going to use all 3 of those. And I'll use my blue pen here. I need 1 boron in the reactants. Okay? So, reaction 1, I have to multiply by what to fix that? 1/2. If I multiply by 1/2, then 1/2 times 2, I'll get 1 boron in the reactants. Okay, let's look at the next one, H2. H2 is in the third reaction. I need 3/2 H2 in the reactants to add up to the overall. So H2 is down here. So I'm going to multiply this by what? Just 3/2. If I do that, then I'll have 3/2 H2 in the reactants. So let's see the last one. I need 1/2 B2H6 in the products. If I look at reaction 2, I have a couple problems. My problems are, first of all, B2H6 is in the reactants, not the products. The second problem is, I have 1 B2H6 in reaction 2 and I need 1/2 of it. Okay? So what do I do to flip reactions? Yeah, I multiply by a negative. So I'll put a minus out there. Okay, now what fraction am I going to multiply by? Yeah, just 1/2. Why 1/2? Because I need 1/2 of those in the products. The minus is what flips the reaction, and then the multiplier matches it with the overall. Okay, am I done? No, because reaction 4 has to have a multiplier before I'm done. Every reaction must have a multiplier. So, since I've exhausted all 3 of those, but I didn't finish all 4 reactions, now I look at intermediates. I need an intermediate. I have 4 choices that appears only twice in all the reactions. What's a good intermediate? You might say O2, but it appears 3 times in reactions 1, 2, and 3. That's not good. I don't like that. Okay. How about B2O3? Okay, that appears twice. However, one of those is not the reaction I'm trying to solve. Does that make sense? I need a multiplier for reaction 4. B2O3 is great because it appears twice, but I already have a multiplier for reaction 1 and 2. So I have to choose one of the waters. Do you want to choose one for me? You like steam better, or do you like liquid water better? Okay, it didn't matter, but she picked liquid water. Okay? So, that's this one. I need this one to cancel with the other liquid water, which is right here. Okay, how many do I have right there?
3/2.
I have 3/2. Look at the multiplier. Is that 3/2 liquid water? Okay, that's in the products. This is in the reactants. Do I need to flip the 4th reaction? No, because I need them to cancel. So I need one of the waters to be on the reactant side and the other in the products, and that's what I have. What do I need to multiply this reaction by then? Just times 3/2. And the products and the reactants will cancel. Okay, I'm done. Because I have a multiplier for all 4 reactions. This was like a medium tough level question, by the way. Yes? What are intermediates? An intermediate is something that appears in the simultaneous reactions, that's down here, that doesn't appear up here. So notice the waters don't appear up there. The O2 doesn't appear up there, and the B2O3 doesn't appear up there. Yes? Nice. If you chose steam, it's actually a little more work, so thank you. The steam one is the second reaction right there. It just involves slightly more thinking. There's negative 1/2 there. So I need this one to be, not negative 1, negative 3/2 right here. So I need positive 3/2 right here, which is what I got in the other method. So it always works. Doesn't matter what you pick. Quickly. Let's start with the molecular, the one in the middle. The molecular is missing what kind of element? It's missing a metal. So they're all non-metals in the molecular. Carbon dioxide is a classic example. And it reminds you, you have to name the subscripts. It's the only one where you name the subscripts. So dioxide, 2 oxygens. Okay? So it has 2 names. It has to end in IDE, and it's always binary for our class. So carbon dioxide is a classic. When you have an aqueous acid, you recognize it because H is in front. So it's either binary, a monoatomic ion, or ternary, like a polyatomic anion. So HCl, hydrochloric acid, is a classic example of binary. It reminds you, if you remember hydrochloric, it's nice because hydro is always the prefix for a binary. Hydrochlor, and then ic is always the suffix. Hydrochloric acid. For ternary, you don't have a hydro as the prefix. So that's just sulfuric acid. Sulfuric because it's the sulfate has more oxygens than sulfite. So the one with more oxygens, sulfuric acid. If it had less, it'd be sulfurous acid. Okay? So no hydro in the ternary aqueous acid. When you get to the ionic, that's the most involved one. So for the binary, a classic example is sodium chloride. It's just the first name as is, sodium, and then the last name has to end in an IDE, like the binary, so chloride. For the ternary, though, it's the first name as is and the last name as is. So sodium is sodium for the first name. That's a sulfate ion, SO4, and the last name is sulfate. So sodium, sulfate, no change whatsoever. It gets a little funky when you have transition metals involved, because for the transition metals, sometimes you can name it in Latin, but most importantly, you have to name the charge. Okay? So say an iron 3 sulfate or an iron 2 sulfate. Gotta name the charge. So we're going to do some examples. That's just a quick overview of how that works. I'm going to make sure you know your polyatomic anions, and you got that pretty set. Let's try some examples here. I'll write these down. If you want to work ahead, feel free to.
I love it.
Not too many good ideas, I think, between that. I just think I would like to get in a better position. Okay. Ooh, these are so good. Okay. All right, here we go. First one's what? Which one of the 3 categories? The acid, yeah, definitely an acid. So, because you see the H in front, so the OBr, or OBr minus, is called what? Which ion is that? It's the hypobromite ion. So, since it ends in the ite, you have to say that's a B. It's bromous, O-U-S, acid, hypobromous acid. Okay, next one. Next one's an ionic. You got a polyatomic cation, polyatomic anion. This is just first name as is, ammonium. Last name as is, hydroxide. Okay, I'm going to skip down a couple. I think this one's the most fun one. No, this one's the most fun one to do next. Yeah. Okay. I'll just think for a second, ask your neighbor, what the heck do they think the name of this is? First, what category is it? And what's the name of it?
Phosphate? I know when there's an H something called.
It's a hydrogen phosphate.
I know when there's an H there's like something.
All right. What is it? If you thought it was an acid, you are incorrect. What is it? It's just an ion. It has a charge. Nice. Okay. It's just an ion. It's on this crazy table in your textbook and in your reader on page 21. It's just one of these to know. Don't drink the Kool-Aid in the wrong way when it has a charge. Even though the H is in front, it doesn't matter. This is hydrogen. Oops, that's a G. Hydrogen phosphate ion. Doesn't really go in any category. It's just one of the ions you need to know. So likewise, the one above it is just a phosphate ion. Now, the one below it with the sodium, that's actually a molecule. It's neutral. It's not one of the ones you memorized, but it's an ionic compound, so this is sodium. Okay? If you didn't get it at first, that's fine. That's why I ask stuff like this, because I know students get confused when they see these things. But this one is sodium, and then hydrogen phosphate. Sodium, hydrogen phosphate. So the next one is an iron hydrogen phosphate. What do I need to add to that? The charge of the iron, which would be 2, since the hydrogen phosphate is -2, and the iron has to be +2 to make it neutral. I could have also called this in Latin what? Ferrous. OUS is the lower charge for iron. What's the higher charge? Ferric, which is +3. +3. So iron could be 2 or 3. Next one, another ionic compound. I have tin here. What's the Cr2O7 called? Yeah, so this is tin. Dichromate. There's also a chromate, which is CrO4. What's the charge on tin?
2.
Well, it's 2 or 4, that is correct. But which one?
2.
4.
Okay, 4. Good. Because chromate is 2 minus, so I need a +4 here because this is 2 of these. -4. Is that okay? So what's the other name for this? Tin4. Standing. Ic, meaning higher of the 2 charges. 4. The lower one's 2. If it was tin2 dichromate, that would be written. That's tin2 dichromate or stannous dichromate. All right, the last one is what category? It's molecular, there's no metal in it. So this is, you name the subscripts in this one. Tetra, phosphorus, as is, and then what's the prefix for 10? Yeah, deca. And you don't need to put two vowels in a row, like deca, oxide, AO. You know what I mean? So you can drop the A from deca oxide, prefix, suffix. You see different people do different things with the vowels, but that's my recommendation. Will you be marked off with two vowels? Probably, unless somewhere in literature somebody uses two vowels. Yes. So there's exception to the two vowel thing. Yeah. So unless you're lucky, I guess, or you happen to know it. Yeah. Go back, rewind. What? Say it again. Why is it hypobromous acid? Which one is it? Oh, okay. It's a ternary, so you don't need the hydro, first of all. And if you look at this, it's this one, the hypohalite ion, BRO, or OBR. And so it's hypobromite. So the IT changes to an OUS.
And we just ignore the H?
The H, this H here, is acid. Yeah, that's what the H goes. Yes. Can you flip the halogen and the oxygen? Yes, you can. It doesn't matter. For all the hypers, though. Say it again. When is the last name ion? That's a great question. Anybody know? At any point ever that it's a non-zero charge. Yeah, good. Yes. Okay, for nomenclature practice, I highly recommend you just go to my YouTube channel. I'm naming examples like one tonight, and just pause before I answer the question. And just see if you can get it, you know, and then watch the video, see if you got the same thing. Yeah. Hydrogen phosphate. Is that also called I don't know if I've heard that before, but that's true for the carbonate and the sulfate. This one has 3, so I don't know. I haven't seen it called the phosphate before. Maybe it is that I haven't seen it. Hey, by the way, it says calculate the molarity of each ion in solution after 30 milliliters of reactant 1 is mixed with 100 milliliters of reactant 2 and another 50 milliliters of water. If you're asked about molarity and you're mixing things of different volumes, yes, you have to sum all those volumes. So you would have to go, in this case, 30 plus 100 plus 50 for your total volume. So you need to find the moles of each and divide it by 180 milliliters in each case. Was that your only question on it? Okay, yeah. So in the other cases, what happened was I just gave you the overall volume. And so we weren't adding specifics. But in that case, you wouldn't have to do that. So I'll repeat again. If you're given 2 items and they each have their own volume, let's say 50 milliliters and 20 milliliters, and you put them together and want to know molarity, now you have 70 milliliters in your denominator. 10. This one right here? Okay. Do 13A, this one, what type of reaction is this? And this one was cupric nitrate and sodium phosphate. What type of reaction is it? Any guesses, anybody? That would be a double replacement. Why is that? Because you have an ionic compound reacting with another ionic compound. So cupric nitrate and sodium phosphate are both ionic. They both have metals.
Wait,
So that would be a double replacement. Did I mark it wrong on that test? C. Yeah, that would be correct.
Wait,
Is that okay?
No.
Oh, you can't see? It's right here. This? This is just the answer to 13a. The net ionic equation, it still came from a double replacement, but when you cancel, what's going to cancel? The sodiums will cancel and the nitrates will cancel out. And so this is left as your final answer. So originally, it would have looked like this. Cupric nitrate, right? Before you did the net ionic equation, it would be this plus sodium phosphate. And that would have been a double replacement. And you'd have to balance it. But that'd be the reaction originally on step 1 of your net ionic equation. But on the answer key, I just wrote the answer. 18a, this right here. This one, you wouldn't be able, I didn't teach that this quarter, so you wouldn't have to do 18a of page 82, 3-methylheptane, pentane, yeah, no worries. This. Okay, that's on page 35. How to write that out? So sodium hydrogen carbonate, that's the first one, reacts with perchloric acid. So I, again, just wrote the answer there. Perchloric acid would have been this. Okay? That'll be a double replacement. That's going to form sodium chlorate, perchlorate, plus H2CO3. The H2CO3 automatically, that's one of what's called a gas-forming reaction, forms CO2 and water. Is that what I got here? Yeah. So that forms CO2 and water, the chlorates cancel, and there you go. Okay, who's next? Okay, there we go. All right, hopefully I wrote it correctly. Let's see. There is one iron, so I just kind of have to work out a little bit. This looks the messiest to me, so I'm going to start here. So I'll just say there's one right now. So that means there's one iron here, there's one iron there. Okay, this will all start there. Then I see what else appears only once. Nothing. Well, maybe a potassium. Where else is potassium? Right there. And then I'm like, oh wait, I'd have to put a fraction because I need a 3/2 times 2 to get 3 here. You see that? Take care. Bye. So I don't want a fraction, so I'm actually going to double this. 2 and 2, and that'll allow me to put a 3 here for 6 potassiums on each side. So I don't have to use a fraction, okay? And then it's just kind of random what you want to go for next. I guess carbon. So how many carbon are on the right-hand side? I think 12, right? 2 times 3 times the 2 in front. So 12. Okay. Then there's in the iron compound on the left, there's 4. You see that? And then on the potassium oxalate, there's 6. 4 and 6, that's 10, right? So how many do I need in front of the oxalic acid right here? There was 12 here, 10 here. I just need a 1, right? Okay? Because that'll give me 12 carbons on each side. All right, next, here you can choose the hydrogens or the oxygens to get the multiplier for the H2O2. They're both painful. Let's choose the oxygen. How many oxygens are on the right-hand side? What'd you get? Did you get 26? Oh, no, not 26. You're right. Oh my gosh. 30. No. 27? Yeah. 3 times that's 12 times 2, that's 24, plus another 3 times 2, 6. 2 of this whole thing, right? 2 of this. There was originally just 3. Okay? How many oxygens are here? Now that you know that. 12? Oh no. Okay, that's unfortunate. Still kind of sticking with the 12. I didn't hear what you said.
Are you talking about just the first compound or the entire compound?
The first compound right there.
Oh, 12.
Well, that's where my pen is, right? Literally pointing at it. 12, right? Okay. That was hard. Okay. I kind of forgot what I'm doing now. Okay. 12 and 4 and 12. 28. Now I totally forgot what this was. 30. Oh, so how many do I have of this?
30.
Yeah, just one. Put one there. Cool. Nice. So it's 2, 1, 1, 3, 2. Fall 13. Conversion. This one. Okay. On it. You would go 21.8 inches cubed. And then you would say, well, there's 1 inch per 2.54 centimeters. And you got to cube that since you need inches cubed. And then there's, for every centimeter cubed, there's 1 milliliter. And then for every 1,000 milliliters, there's a liter. Is that okay?